Next talk is by Tobias. If you can join. So Tobias is a PhD student at RPTU Kaiserslautern-Landau, and the floor is yours. Sorry.
Yeah. Thanks for the introduction. I'm very happy to present you our work on VeriCHERI today, which provides exhaustive security verification for CHERI processors. And this work has been conducted involving a lot of collaborators that you can see listed here. What was our reason to do this work? So in today's computing systems, we heard it a bit in the last talk already, there's one of the main goals to provide robust and trustworthy security mechanisms. And one major challenge in this area is the topic of memory safety. There have been quite some famous bugs in recent years that compromised memory safety and security and also led to some very costly fixes. And one of the solutions that have been proposed to deal with this topic are capabilities, or in the concrete case, CHERI. CHERI stands for Capability Hardware Enhanced RISC Instructions and can provide fine-grained memory protection that is directly enforced in the hardware. CHERI is also gaining a lot of traction in industry at the moment, so there have been projects by ARM, by Microsoft. You will also recognize a lot of posters if you walk around here, for example, by CodaZip, or also open source designs by Cambridge University. So it's a topic that is evolving fastly. For all of you who haven't heard about CHERI so far, the basic idea is if you take a classical memory and, for example, you store an array in that memory, then at a low level you use a pointer to access some address in this array. But if you would now add an offset to a pointer, either maliciously or maybe just by accident, then you could run into a totally different part of your memory where you maybe shouldn't read from or shouldn't change anything. CHERI now is taking the approach of using a capability instead of a pure pointer. And with a capability, you not only have the address that you want to access in the memory, but you also get bounds, like an upper bound and a lower bound of the memory region that you're allowed to interfere with. And you also store some additional permissions in this capability. So in the end, a legal memory access will always require you to have a valid capability that holds the corresponding permissions, for example, whether you want to write or read, and whose bounds include the requested address. So this is quite a nice technique, but still involves some challenges. So if we want to use that and also be sure that our system is secure, then we need a comprehensive security verification so that in the end we can provide trust for the entire system stack. From a hardware point of view, there already have been some related formal verification approaches. Two of them verified the system based on a formal ISA model, which was rendering quite some manual effort, and a very recent publication involved the automatic generation of functional properties based on the sales specification. Still, there are some pitfalls involved with these methods. If you manually translate the security properties to verify them on your design, then it might be that you do not cover every aspect or every corner case. And also, if you do your security verification on a time abstract ISA model, then you might also miss non-functional vulnerabilities, which might include timing side channels or transient execution side channels. So with VeriCHERI, our goal was to provide a global security objective containing confidentiality and integrity, which means not reading from any part of the memory where you're not supposed to read, and also not changing any data that you're not supposed to change. and for that we use the timing-accurate RTL implementation of a design. To implement this verification methodology, we first needed to define an attacker model. So if we assume that we have a processor that is connected to a memory, then we have several tasks running on that processor that are all supervised by a trusted entity, for example, the operating system. And now, among these tasks, we have one malicious task that tries to break out of its capabilities and either read or change memory addresses outside that. And to now prove our security goal of confidentiality and integrity, we need to find a suitable approach for this. And here we chose to model our security objectives using so-called non-interference. Non-interference is a very strong notion of security and is also well known and widely adapted in the security community already. How does non-interference provide or define our security? So if we go back to our processor with the attached memory, we now can divide our memory into a public part and a protected part. So our process has access rights to the public parts, but not to the protected parts. And then everything that we have access to is denoted as so-called low locations, and what is protected from our process is denoted as high locations. And now we have non-interference if we can prove that the high locations do not influence the low locations, because in this case it would not be possible to either read from the protected memory addresses or to change something there. Based on this, we derived a formal model and we set up two CTL properties, one for confidentiality, one for integrity, that you can see here. I don't want to bother you with the math, but from now on there were some steps necessary to transform these CTL properties into properties that we can run on like commercial solvers. And how we did that will be presented in the next slide. So for our interval properties, we first defined a protected address anywhere in the memory that was left to be chosen by the solver. So we had one specific protected address that was symbolic, so any value could be chosen for that address. We also defined that there will be memory regions where the attacker capabilities grant access to, and there will be memory regions where the attacker capabilities deny access. But the only constraint that we applied here was that our protected symbolic address must always be included in the memory regions where the attacker capabilities deny access. Everything else, which address was chosen and how the exact bounds of the capabilities were set, that was left to the solver. With the help of this, we could define several macros that we used in our verification and then ended up with our properties that you can write in SVA, for example. Again, we have one property for the confidentiality and one property for integrity. And basically, these properties say if we have a symbolic address that is protected by CHERI capabilities, then the system must either not send a read or write request, or if we do a read or write request, then this must not go to this symbolic protected address. And some of you maybe already recognize that these properties now describe the behavior of CHERI and the security properties in a single clock cycle, which leads to very scalable proofs because we don't need our solvers to unroll for a very long time. And also by our symbolic macros, we can cover every possible compartmentalization, and by our initial state also cover every possible program that you could run on the hardware. The question is now, what is if one of these properties fails? In case of the integrity property, this would already be a violation to the security. In case of the confidentiality property, the property that we saw here is a sufficient condition, but not a necessary condition for security, because there could be the case where protected data is first read and propagated to internal buffers that are not yet attacker visible, and then some security check interferes and erases the data without causing a leakage. So in this case, we need to define a less conservative two-safety property for confidentiality that covers exactly these scenarios. And we did this by reformulating unique program execution checking that was originally designed to detect transient execution side channels. And we reformulated that in a way to match our CHERI-specific threat model. After defining all of these properties, we also conducted a case study on the CHERIoT Ibex processors. You can see the results here. We ran the properties one after another. So first we ran the one safety integrity property, which already discovered 2 bugs that are listed here. That are listed here. And after fixing these 2 bugs, the property was holding with a runtime of only 7 minutes. After verifying the integrity, we went on with the one safety confidentiality property. Here we had to distinguish between reading from the data memory and reading from the instruction memory. For the data memory, there wasn't any problem, so the property was holding immediately. For the instruction memory, though, there was a counterexample that showed that it was possible to fetch an instruction from outside the PC capability bounds. And to further evaluate this, we needed to apply UPEC-CHERI, which then ultimately also confirmed that there was a side channel that could create a timing-dependent behavior based on the exception of the fetched data. We can shortly have a close look on this in detail. So this more or less comes down to a potential transient execution attack. We branched to an address outside the PC capability bounds. Then the core correctly raised an exception, but the exception handling was delayed based on 2 bits of the data that we just fetched. And by this delay, we could influence the performance counter, again, based on 2 bits. And this allows us that by measuring the execution time, an attacker could probe any arbitrary memory address for these 2 bits. Our finding has also been confirmed and then later fixed by the CHERIoT development team. And in the end, this proved that VeriCHERI is able to detect several also new and unknown security issues. It showed to be a scalable, iterative verification flow, and the symbolic verification IP that is CHERI-specific that we developed for CHERIoT can also be reused for similar designs. Currently, we're also extending this work to other CHERI open source cores, like from the BlueSpec family, CHERI Flute, CHERI Tuba, and I hope that we can present some results on that in the future. If you're interested on further details, then we invite you to come to our poster in area 2.3. We also have a publication which was published at last year's ICCAT that you can find here, and also the CHERIoT Ibex team offered us to write a blog post on our detected vulnerability, which you can find here. Thanks for your attention.
Yeah. Thanks a lot, Tobias, for a very nice talk and also for keeping time for questions. So we have time for one or two questions. Please raise your hand, if any. Okay, it was certainly very, very clear. Okay, thanks to the speaker again.